Hello, dear fellows. I'm Jinri Tan from German Aerospace Center. Today, I would like to share my recent research solving a translation mode detection problem with a deep CNN-BiLSTM model. First of all, I want to explain the background and the problem definition. Translation mode detection can contribute to urban and traffic planning from the perspective of traffic managers and could also provide customized routing suggestions from the perspective of road users. A transportation mode detection problem is detecting transportation modes among steel, car, bike, walk, bus, train, and so on with collected smartphone sensor data. Please look at this figure. Once sensing data are collected, the data go into data processing step, and then train in a deep learning model. Finally, a test data item can be classified into different translation modes. The contribution of this research is using fewer sensors and computational resources compared to much previous work, obtaining comparable research without using feature extraction and post-processing such that the workload of this model is relatively light. Before we start the data pre-processing, we would like to introduce the dataset first. The dataset used in this paper is the SUSEX Huawei Challenge Dataset 2018. This dataset is collected by a single participant with a fixed smartphone position but no fixed orientation. Data of 7 sensors are collected. The participant recorded 271 hours data as a train set and 95 hours data as a test set. Each sample covers a 1 minute non-overlap time sequential data with sampling frequency 100 Hz. The task is to recognize 8 different translation modes. Here is the distribution of different translation modes on train set and test set. We can notice that the data of different translation modes are not balanced, and these two distributions are also not the same. Although SHL dataset has data from 7 sensors, it doesn't mean that we must use them all. In previous research, accelerometer, magnetometer, and gyroscope are the mostly frequently used. In our paper, we only use accelerometer and magnetometer measurements as inputs. The figures are examples of magnetic fields in x-axis for different translation modes, and we can see the figures of car, subway, and train are really very different from the other translation modes. Now let's do data pre-processing. The first step is slicing data. The original time window is 60 seconds and non-overlapping. We will explore whether different window sizes can improve the performance. Later, let's show the results of different window sizes. Then is data smoothing. For each axis, we take the average value of every 5 data items. If the data items is at the beginning or at the end, for example here, the average value of 3 data items goes to the next step, and here is the same value as before smoothing. So the third step is downsampling. We will test different downsampling frequencies. Here is only one example. Show that every 2 data items are merged into one, and that means the mean value is taken. So in this case, with the downsampling frequency is 50 Hz. The last step is calculating magnitude and jerk. These two equations are how magnitude and jerks are taken. After data pre-processing, we start to build up the model. The figure shows an overall structure of our model. There are six input data. There are acceleration data from XYZ axis, acceleration jerks from XYZ axis, acceleration magnitude, and the same as the magnetic fields. So in total, 6 channels are in our model. And finally, the samples are classified into 8 modes. Let's introduce the details of CNN-BiLSTM model. So as each channel has the same components, we only show the details of one channel on the right side. After batch normalization, a one-dimensional convolutional layer with a ReLU activation function is ended, followed by a max pooling layer. Then a convolutional layer and a max pooling layer are ended without batch normalization. Later, batch normalization, convolutional layer, max pooling layer are ended, and they repeat 3 times. After that, 6 channels are concatenated and continue to a BiLSTM layer. After 2 fully connected layers, the probability of different modes are obtained. The final fully connected layers use softmax function as activation function, and the rest of layers only use ReLU. The loss function here is mean squared error, and L2 regularizer is applied to a warm overfitting. You can find the parameters in detail in our paper. The most exciting step is experiment. The original chain set is split into a sub-chain set and a sub-validation set. To a warmed overfitting, an earlier stopping is set. The batch size is 100 and an adaptive learning rate is set to get better performance. Matrix in this paper is accuracy and F1 scores. And the average value of 10 chaining are recorded to avoid the influence of random initial starters. As mentioned, different time window sizes and downsampling frequencies are tested. The figures on the left is accuracy. With the window size increases, the accuracy also increases. When the downsampling frequency is only 1 Hz, the accuracy is relatively low, and then the accuracy is a bit stable. When the window size is 60 seconds, and downsampling frequency is 100 Hz, we get the highest accuracy with a value of 91.21%. The figures on the right side is F1 score. The trend of F1 score is similar as that of accuracy. The best F1 score we got is 90.4% when the window size is 60 seconds and downsampling frequency is 20 Hz. We select a confusion matrix from one chain model. In this training, the F1 score of walk, run, bike, car perform well with a value more than 90%, but F1 score of train and subway got low F1 scores as they are a bit similar. Let's also compare our model with previous work. First is the comparison with deep learning models. Although we don't overperform the work of Jaroszewski, we use less inputs and a light model and no post-process, so we think we got a very good result. We also compared with the results of machine learning models. Similarly, we use fewer inputs, whereas get a comparable F1 score. Finally, we draw a conclusion. We develop a light deep learning model to solve a mold detection problem using fewer sensors and simpler processes, but obtain comparable F1 scores and accuracy. Thank you for watching. If you have any questions, please contact me via email on this slide. Last, as a young editor of Journal of Traffic and Transportation Engineering, I shortly introduce this journal. The scope of this journal includes traffic engineering, infrastructure engineering, and automotive engineering and related fields. All submissions fit for these fields are welcomed. Thank you.